All right. Oh, sorry, getting started just a minute too late here. Okay, so we are starting chapter 14 today. Okay, Riley's helping me out by passing out the participation questions, and then I print out some of the examples for today, though I don't know if I printed enough copies for everyone here, so if there aren't enough, I apologize. Yeah, sorry about that. I'll print them out later. They're also available on Canvas as well. But yeah. And so for those who are online right now, you can also check out the chapter 14 examples on Canvas. Let's see here. So, right, the homework for chapter 13 is due by today. Right, there are on sampling. There's like the homework, and then there are like additional problems for the chapter. Those I put the same due date, just as like to make them consistent with the homework. But those aren't graded. Additional problems are not graded whatsoever. You don't have to do them. Never have to look at them. They're just there for additional problems if you want to do them. Okay. So yeah, so trying to think other announcements. Right, in a week from Wednesday, I believe. I guess I can look at the calendar. Right, so yeah, a week from Wednesday we'll have our first exam. Okay, it's just a reminder for people. Now, that exam will be given on Wednesday as well as the following Monday. So for you guys, the exam is going to be 2 weeks from today. So it will be covering chapters 12. Is that the first chapter we do, or is it 11? I forget what it is in the book here. Yeah, chapter 12, 13, and 14. Okay. There are practice exams online. Now, I think for the practice exam 1, it covers some of chapter 14, but not all of it. So you're going to want to look at exam 1 and 2, okay, to also look at some chapter stuff because of the changes in the class. There's one less regular exam, and so what's covered on the practice exams is not necessarily the exact same thing as what's covered on the exams for this semester. Okay. So take a look at practice exams 1 and 2. Okay. Right, the quizzes are on Canvas. Right, are also, I believe I've changed them so that there is no like you can look at them at any time. Okay. I believe if you retake it, it shouldn't change your score or update your score or anything like that. If it does, let me know, and then I'll try to fix that so it doesn't do that. But yeah, but I want to try to have those there as an option as other practice for people who want to do it. And then otherwise, right, there's the different examples we do in class. You can look over those, try them yourself, right? If you haven't looked at them in a little while, try taking the questions right off of Canvas and doing the questions yourself, and then checking the answers. Maybe going through the lecture videos to look at it worked out. If you're not sure how the answer is obtained. Okay. Any questions? Is there a key? Yeah, the practice exam should have a key. I will double check that, but I believe there's a key for the practice exams. If there isn't, I'll make sure they're posted. But yeah, key for practice exam should be there as well. There should be a blank and one with an answer for them. Okay. Other questions before we get going here on chapter 14? All right. Okay. So chapter 14 is the discussion of chemical kinetics. Okay. Right. So the first thing we need to ask ourselves, what are chemical kinetics related to? And that is talking about the discussion of rate. Okay. Chemical kinetics is related with rate, related with speed. Right. And so first kind of question here is, what is like a rate? Example, either in chemistry or outside of chemistry, right? When we talk about rate, right, what pops into your head?
Change in value over change in time.
Huh?
Change in value over change in time.
Value over change in time, right? Or rate, just like speed, right? How fast you travel in your car is a change, right? For physical speed, right? We think of change in distance over change in time, right? In general, some rate is referred to as change in value over change in time. And so in chemistry, right, what change are we looking at over a change in time? Change in what over a change in time for chemistry here? Yeah, so what's changing in the reactions? Right, when a reaction's going on, what's being changed? The products, right, and the reaction, and the amount of those is changing over a change in time. Now, often we'll talk about concentrations here, right? So we'll often refer to changes in concentrations, okay, over a change in time, but you could think of a change for moles or things like that. Often we'll refer to concentrations here, right? So for right, for chemistry, right, a rate, the rate of a reaction related with the change in concentration, the reactants, products versus a change in time. Oh. Okay, there we go. Right. So, right, that roughly, right, that's what we're referring to when talking about chemical kinetics, right? Kinetics is the study of rates. Okay, and so chemical kinetics is the study of chemical reaction rates, right? So we use this all the time in labs, right, to understand not just how fast a reaction goes, but how we might be able to speed it up and slow it down. And as we'll get to another day, we'll talk about reaction mechanisms and things like that. Understanding the rates of a reaction can help us understand how that reaction is taking place, how things might be reacting, and things like that. And that's related with reaction mechanisms, and those are very much tied into the study of reaction rates. Okay. So we're going to look at a graph, and we're going to answer these questions, right, about looking at how does the concentration of reactant change with time, how does the concentration of products change with time, and then how do these things relate with each other. So we have our overall chemical reaction here, N2O5 here. And right, so 2 N2O5 going to 4 NO2 plus O2. Okay. And so again, what we're interested in thinking about is how is the rate of consumption, right, the rate of change of the reactants, like what is that, right? What is the rate of change of our different products, right? And how can these be related with each other? Okay. Focus in specifically in this kind of time interval here, 300 to 400 seconds. Okay. Right, and so we'll kind of look at this, right? So given kind of the data in this picture, right, and we're looking at this time interval from 300 to 400 seconds, right? What is the rate? Like, how much is the concentration of N2O5, right? The rate of consumption. What is that over that 100-second time window from 300 to 400 seconds? How would I get that? Right, how would I get kind of the rate change of the concentration of N2O5 over that 100-time-second window from 300 to 400 seconds?
Divide that change in N2O5 over the 100 seconds.
Yeah, right. So what we want to be doing is we want to take, right here, I'm going to write down something and then I'll flip it over. Right, and so right, if I want to look at what is the change concentration, new shape, that's what I'm looking for, right? Right, if I'm looking at the change in concentration over some change in time of my reactant, N2O5, right, plugging in those numbers, right, that will give me how quickly N2O5 is being consumed, right? Or often so when we talk about these things, we might talk about the rate of change of the concentration, right? Right? Or for reactants, we'll talk about often the rate of consumption, okay? So how fast is my N2O5 being consumed, right? And it's the change in concentration over some change in time, right? Again, our rates are a change in concentration over a change in time. Here we were looking at a time interval of 100 seconds, which was that 300, 400 seconds, right? And the concentration change was written on the figure was minus 0.0019 molar, right? So this rate of consumption of N2O5 is related with 1.9 times 10 to the minus 5 molar, okay? Right? That is my rate of consumption of N2O5, for example, right? That's how we kind of describe that. That's how we talk about it. Say that is the rate of consumption, N2O5. Okay? Oh, did I forget to write that negative? Yes, I did. Sorry. Yeah, that's a negative, right? Yeah, the negative should still be there. I didn't do anything to get rid of it. I just forgot about it. Thank you for pointing that out. Yeah. Oh my gosh, yeah. Thank you. Yeah, we'll flip back to that. Oof. All right, a couple of little mistakes early on. Try to avoid that in the future, right? So let's look at, say, like NO2 here, right? So NO2, you do the exact same thing, right? If we wanted to look at, right, the what we call the rate of formation of NO2, right? Again, the rate of formation, right? Rate of consumption, rate of change, these are all referring to similar things, okay? So we're looking at change concentration of NO2, right, over change in time. Again, is then that 0.0037 molar over 100 seconds, which will give us 3.7 times 10 to the minus 5 molars per second. Okay. Oh, pull that up a little bit, right, so we can see that. Right? And so, again, right here, we are looking at the rate of formation of NO2, right? The rate of change of the concentration of NO2, its rate of rate of change of concentration of NO2, right? And again, it ends up being 3.7 times 10 to the minus 5 molars per second, okay? So they just take the change in concentration and divide it by the change in time. Okay. So again, right, rates of reactions are related to rates of changes of concentrations over changes in time. Okay, so again, whenever we talk about rates in this class, that's what we're referring to, rate of changes in concentrations over changes of time. Okay. So now the question is, right, how might these things be kind of related with each other? Okay. So this value of minus 1.9 times 10 to the minus 5 and value of 3.7 times 10 to the minus 5. Like, I guess what I'm looking here for here is, right, actually, let's keep it here. Right, what sort of, are they equal to each other? Is one potentially twice as big as the other, 3 times as big as the other? You know. Yeah, right. So, right, I mean, kind of ignoring the negative sign, right? The negative sign is just telling us that we're losing the concentration, but the magnitude here, 1.9 times 10 to the minus 5, is half that roughly of 3.7 times 10 to the minus 5, right? Right, round it up. Multiply this by 2, round up, and you get 3.7 times 10 to the minus 5. Okay, right? If we go back to slide here, okay, you'll see here that the change in concentration of O2 is 0.009 molar, or that same change in time interval of 100 seconds, okay? What you see, right, this is roughly half of N2O5. It's 4 times less than NO2, right? So all of these things are related to each other, and these rate of changes are related to each other based off of our balanced chemical reaction here, right, in the stoichiometric coefficients and that balanced chemical reaction, okay? Right, so we just kind of talked about that N2O5 gets formed or gets consumed twice, like half the rate of NO2, or NO2 gets formed twice as fast as N2O5 gets consumed. Okay, and that makes sense based off of our balanced chemical equation here, right? We have 2 N2O5 forming 4 NO2. Right? So if that's occurring, right, that means every 2 moles of N2O5, I form 4 moles of NO2, right? So NO2, its concentration should increase twice as fast as N2O5 is decreasing, right, just based off of this balanced stoichiometric coefficient, right? Similarly, every 1 mole of O2 that I form, I should be getting 4 moles of NO2, right? So NO2 is forming 4 times as fast as O2, right? So my rate of formation of O2, right, or of NO2, I should say, my rate of formation of NO2 is 4 times that of the rate of formation of O2, okay? So, right, the rate of change of your concentrations of your reactants and of your products are related to each other based off the balanced stoichiometric coefficient in your chemical reaction. Right, and again, we can just think about that conceptually about the fact that, right, it is saying, right, these coefficients are telling us, right, I form 1 mole of this, how many moles of this do I form or do I lose, and things like that, right? And those then are directly related with the rate of changes. Okay. Questions about this? All right, then. So then based on the following reaction, the rate at which ammonia is formed is blank that of the rate that nitrogen is used. Is it the same? 2 times that? Half that? Or 3 times that? Right. And as a reminder, right, ammonia, NH3. Okay. What do people think? I heard something times, 2 or 3, 2 times, right? B here, right? Yeah, so it is going to be 2 times that, right? Because, right, the rate of the relationship between these rates is given by the balanced stoichiometric coefficients, right? And if I say lose one of these, lose one of N2, I got to form 2 NH3. So the rate of formation of NH3 is twice that, or 2 times that of the rate of consumption of N2 here, right? So it is B 2 times, okay? So, right, again, by the balanced stoichiometric coefficients. Question? All right, so now with some numbers here, based off of the balance following reaction, right? If the rate of formation of O2 is 0.015 molars per second, what is the rate of disappearance of NO2? A, B, C, or D? We need more information to solve the problem. B here, right? Right, so if we look at this balanced chemical reaction, right, we can say that based off the stoichiometric coefficients, right, that the rate of formation of N2O5 should be twice as fast, or sorry, the rate of disappearance of N2O5 should be twice as fast as the rate of formation of O2. So I should have that rate of formation of O2 is times 2 gives me the rate of formation of N2O5, okay, which gives me B, 0.03 moles per second. Okay. Right.
Could you explain that a little more, please?
Yeah. Right. So let me write out the reaction here. 5, 4, 2. All right. Let me share. Okay. Right. So again, right, what we're given in this problem is we're given the balanced chemical reaction and the change of concentration of O2 over some change in time. And our question is, what is the change in concentration of N2O5 over that same change in time, right? What does that equal? Okay. And I know that this should be related with the balanced chemical reaction again, right? Because again, right, this balanced chemical reaction tells me, right, if I gain, say, 1 mole of O2, I lose 2 moles of N2O5, okay? Right, and what this rate is telling me is, say, in 1 second, I gained 0.015 molar concentration of O2, okay? So in that same time frame of, say, that 1 second, my concentration of N2O5 has to decrease by twice the amount, okay? Right, so that the change concentration of N2O5, change in time, right, is going to be equal to 2 times change concentration of O2, change in time, okay? Right, and so it's 2 times that, which gives me the 0.03. And again, it's 2 times that because I have the stoichiometric coefficients here of 1 versus 2, okay? Right? Every one of these that I gain, I lose 2 of these N2O5s. So, right, again, if every one of O2 that I gain, I lose 2 N2O5, right? So the rate of change of N2O5 is twice that of O2, right? The larger the stoichiometric coefficient is in your balanced chemical reaction, the faster that thing is being consumed or produced, right? Because just the more stuff is being used up or given off, right, in your chemical reaction as the reaction is taking place, right? Again, if we think about just, I like to think about, right, I have 1 mole of, O2 being formed. If I form 1 mole of O2, I would form 4 moles of NO2, and I would lose 2 moles of N2O5, right? So this is often how I try to think of these type of problems, where I'll say, right, right, 1 mole O2 formed means that, right, right, if that's the case, that means 4 moles of NO2 are formed, right? Because of my stoichiometric coefficients, if 1 mole of this is formed, 4 moles of that has to be formed. Here, I'll move this stuff up again, right? And then, right, and if 1 mole of O2 is formed, then 2 moles of N2O5 are used, right? Are consumed, are used, right? And then this tells me kind of these relationships, right? That 1 of these gives me, say, 4 of these. So the rate of N2O5 is 4 times that of O2, right? And similarly, then the rate of, of NO2, right, before. The rate of N2O5 is 2 times that of O2, right? The rate of NO2 is 4 times that. And we'll see another way of how we can develop these relationships in just a minute. We talk about the average rate of reactions. I'm kind of waiting until we get there to kind of present that. So questions about this problem, about the relationships between the rate changes of your reactants and products, right? They're just purely based off of their stoichiometric coefficients. All right, here. Oh. Oh shoot, all right, I skipped that slide. So let me add a slide here. I accidentally deleted a slide apparently. All right, so the average rate of reaction let me restart now. Oh, yeah. Sorry, getting all this stuff squared away with Zoom. All right, here we go. There we go. Back here. Right, average rate of reaction. Okay, so we've been talking about, right, in these different problems and things like that, right, the, say, rate of formation of O2 or formation of NO2 or consumption of N2O5, right? But again, we see here, right, all of those 3 things are different. Okay. Now, if I'm working in a lab and I, am measuring this chemical reaction N2O5 going to NO2 plus O2, right? I'm measuring that chemical reaction, and in lab, I have stuff set up to where I can measure the concentration of O2. So given that, I'm able to measure what the rate of formation of O2 is, and I say, all right, I got the rate of formation of O2, that's how fast my reaction goes, I report that, write a paper on it or something like that, right? Share it to the world, right? Tweet it out or whatever, right? This is the rate of formation of O2, right? The rate of my reaction, N2O5, going to NO2 and O2 is given by the rate of formation of O2, okay? But then someone else somewhere, right, decides they're going to measure the rate of this reaction, but they have a setup to measure the rate of N2O5 instead of O2, okay? Well, they're going to measure a different rate than what I measured, even if they have the exact same setup, right? They have all the same reaction conditions, everything's the exact same, but they pick to measure the rate of consumption of N2O5 instead of the rate of formation of O2, they will get a different rate, right? Because as we talked about, right, the rate of consumption of N2O5 is twice that of O2. So then this person tells me, hey, the rate of the reaction is twice as fast as what you measured it, right? You're wrong. And then we're going to get into a big fight. And the thing is we're both right. The reaction is taking place at the exact same speed. It's just depending on whether or not you're looking at one of the reactants or one of the products can change your answer if we define the rate of the reaction as just, say, the rate of formation of one of the products or reactants, okay? And so we don't do it that way. Instead, what we do for some reaction, right, is we define the average rate of reaction, okay? Right, I'm going to pick just some general reaction, A plus B going to C or something like that, right? So whatever stoichiometric coefficients, A, B, C. Okay? Right, for this, my rate of my reaction, I'm just going to call it rate here. So often, right, if you're talking about the rate of reaction, you're talking about the average rate of the reaction. It's the same thing, okay? Just to simplify things, right? We just say the rate of a reaction, not necessarily saying the average rate, okay? So if I talk about the rate of a reaction, right, the average rate of reaction, that is going to be defined related with that rate of change, or say the concentration of A over some change in time, times 1 over its stoichiometric coefficient, in this case, negative 1 over that stoichiometric coefficient, okay? And that is going to be the same thing as, say, 1 over the stoichiometric coefficient of C here, times the rate change in concentration of C over change in time, okay? And that's also going to be the exact same thing as minus 1 over B times change in concentration of B over change in time. So these minus signs here that appear for my reactants, right, A and B are reactants. Minus signs that appear for the reactants are there because the average rate of the reaction is defined as a positive value. It could always be positive, okay? But the rate of change in the concentrations of my reactants is always negative, right? Because I use up my reactants over time, so the concentration decreases with time, okay? And so that's where the minus sign comes in for the reactants, right? There's no minus sign on the products because it's a positive rate of change, right? The products are being formed over time, so it's a positive value, okay? And so if I define the rate of the reaction as such, then no matter what I look at, I will get the exact same rate, okay? Because let's look at our example again for N2O5, to those forming the 4NO2 plus O2, right? That was our reaction, okay? Right, if I define the rate of the reaction as, right, in my example I talked about, oh, well, if I measure its concentration O2 over change in concentration time, and I multiply it by 1 over the stoichiometric coefficient, which happens to just be 1, right, then I measure some rate, right? And then if I measure instead the rate of change of N2O5 with respect to change in time, right? If I multiply this by minus 1 over its stoichiometric coefficient, okay, this will be the exact same thing. Because as we talked about earlier, right, the rate of change of N2O5 over time, right, is going to be twice the change in O2 over time, okay? And because of the fact that these things are related, right, by their balanced stoichiometric coefficients, okay, right, if I just divide the rate of change of my concentrations of my reactants or products by their stoichiometric coefficients, then I will get the exact same number no matter what thing I measure, okay? And we define this as the average rate of reaction, okay? Again, we do this so that no matter what you're measuring in lab, you will always get the same average rate of reaction as anybody else, as long as they're, like within the same reaction conditions, okay? That it does not depend on whether I measure N2O5, NO2, or O2, okay? My average rate of reaction is the same, okay? Because I take these rate of change and I divide them by their stoichiometric coefficients in order to make it so. Okay. Questions about this average rate of reaction? Sample and going over this concept here. All right. So actually, no. Let's look at, say, this problem here, and then I'll just kind of make up another one in a second here. But in this problem, right? Let me instead ask, what is the average rate of this reaction? Okay. What would the answer be, right? So again, the question here instead is, right, what is the average rate of the reaction given the rate of formation of O2 is 0.015 molar? Right, so what do you think? If, right, I have the same thing, right, balanced chemical reaction, rate of formation of O2 is 0.015 molar. What is the average rate of this reaction? Would you say it's A, B, C, or D? A, right? Because the average rate of reaction is going to be related with the rate of formation of O2 divided by its stoichiometric coefficient, which happens to be 1. So you take 0.015 molar per second, and you divide that by 1, and that gives you A. Okay? So another example with this, right? Let's say I have that exact same chemical reaction, but now what we're given is the rate of change in the concentration of N2O5, right, is negative 0.24 molars per second. Question is, right, what is the rate of change in NO2 over time? And then what is the average rate of the reaction? Think about it for just 1 minute, and then we'll answer this together. All right. So what is the change in concentration of NO2 expected change in time? going to equal? Oh, shouldn't move that, sorry. Zero 0.48 molars per second. Okay. Right, because based off our balanced stoichiometric coefficients, every time I lose 2 of these, I gain 4 of these, right? So the formation of NO2 is twice as fast as the consumption of N2O5, okay? So, and then the rate of change of N2O5 has to be a positive number, right? So not negative because it's a product, right? This is negative because it's a reactant, okay? So the positive, 0.48 molars per second, right? Just 2 times this value, right? Change concentration of NO2. Change time is twice. I guess times a -1. If we want to keep track of our negative signs here, delta N2O5, delta T. Okay. Right. Now, what about the average rate of the reaction? What is that going to equal? So 0.12 molars per second, right? And we get that, right, by doing the rate, right, by saying the rate equals -1/2 times the change concentration of N2O5 over change in time, right? So we multiply this change concentration of N2O5 by -0.5, get the rate of the reaction, right, which is 0.12 molars per second. Okay. Right. So all these questions relating rates of consumptions and formations and rate of changes and rates of the reaction, all of these problems, right, are all about the balanced chemical reaction and the stoichiometric coefficients relating the different reactants and products that you have. Okay? Any questions about this example here? All right. So we'll do an example here. Chapter 14 examples. So here, right, this is maybe something what you would do in lab where, right, so I have a version of this, right, where I'd say, okay, in lab, right, I have this chemical reaction. I measure the rate of disappearance of H2, okay, by measuring, right, at different times, what is the concentration of H2, right? And so, all right, first thing we'd like to do here is we want to calculate the average rate of the reaction with the time interval between each measurement, right? Right. I guess we haven't talked about it, right? But the H plus ions come from here. Okay. I forget we haven't talked about acids and bases, right? This is a strong acid. It will break apart into form Cl minus and H plus. So H plus ions come from the Cl. HCl in that balance come in that chemical reaction, right? So this balanced chemical reaction, that's where that's coming from. So the first question, right, is how is the rate of the reaction related to the rate of change in the concentration of H plus? All right, my reaction's at CH3OH plus H plus Cl minus going to CH3Cl plus H2O. So how is the rate of the reaction related with rate of change of H plus? Say that again? Yeah, it's going to be equal, right? There will be a minus sign, right? Because this is a reactant. So, -1 times this is my rate for my reaction, right? Oh yeah, but the magnitude will be equal, right? Stoichiometric coefficient of 1. So I just divide by 1, which gives me the exact same number. Okay. And so then how do I get, say, the change in concentration, right? This rate of consumption of H2, right? The rate of change of H2, right? For, say, this time interval here. How would I calculate that? Right? Yeah, so I would need to take the time difference, and what else do I need? Right? What else? So I need the time difference, and then I need the concentration difference, right? So for this first set, right, if I look at the interval between reaction 1 to 2, here, so I try to label these 1, 2, 3, 4, 5, right? Okay, right? At change in concentration of H plus over change in time, it's going to equal 1.67 minus 1.85 divided by 79 minus 0. Okay. Sorry, I'm going to go back to that. Just going to write out what that equals. Okay. All right. Right. So that equals minus 0.00228, and that's going to be molars per minute. So in this case, right, the time is given in minutes. And so the time here I have is per minute. Okay. I can convert it to seconds, right, by using 60 or whatever divided by 60 and convert that to seconds. But I'll just leave it in minutes because that's what's given, right? And so that is right negative 0.00228 is that, right? So the rate of the reaction, right, for this time interval, right, it's just a positive 0.00228 molars per minute, right? So that is the rate for the time interval, right, between the measurement, the first measurement and the second measurement, right? I can then repeat this, right, for say, right, for measurement 2 to 3, right, delta H plus, right, over delta T, right, is then 1.52 minus 1.67 over 158 minus 79. Okay. And that gives us a value of, so that equals minus 0.00190 molar per minute. Oh. Right. Right, which again, then the rate of the reaction is just the positive value of that because of the fact that our stoichiometric coefficient, right? Positive, so. Okay. Right, and then you can repeat that process for steps, intervals 3 to 4 and 4 to 5, right? And if you do that, right, then you'll get these values here. So here I have written the change in concentration of H over change in time for these different time intervals. That's why they're all negative, okay? But the average rate of reaction between each time interval, right, and It's just the opposite sign, right? It's the positive value of these different rate of changes. Okay. And then here I calculated the average rate, right? I just took the average of those four numbers to get the average rate for the entire experiment. Okay. That wasn't really asked, right? What was asked is just getting the values here on the right. Okay. So questions about this example, right? How would I calculate these rates of formations and consumptions and rates of reactions based off of concentration and time data? Any questions? All right. Right. So this example, right? Write the rate expressions. Okay. So this is talking about how the rate is related to the rate of formations and rate of consumptions, right? Rate of changes of your reactants and products here. Right. 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 This was the question, right? Write the rate expressions for this reaction, okay? Which is, rate equals something, right? In terms of change in concentrations over change in time. Right. What is that?
Are you using any of the variables that
Actually, for all of them, like,
okay.
yeah. Sorry.
So for O2, but
Mm-hmm. Yep. So O2, right, is the same. NO2, you have to multiply by 1 over 4, and N2O5, right, minus 1 over 2. Yeah. Right. So again, that's how we relate the rate of change between all these guys and the rate of the reaction. Right, and then you can even use this to relate the rate of change between these two, right? Again, using this, I can say, oh, right, so the change of concentration of O2 over change of time is minus 1/2 change in concentration of N2O5 over change in time, right? So if I'm given this, I can multiply it by minus 1/2 to get this. Or sorry, multiply it by minus 2 by moving that over, but yeah. So like, right, so you can use this relationship as well to relate the concentrations if you want to. Yeah. But yeah. Right, so again, the rate of the reaction, right? Right. Once you kind of remember it, it's a very simple formula, right? It's just change of concentration and change of time of whatever reactant or product divided by their stoichiometric coefficients, right? And then for reactants, you just got to multiply by a minus sign because its concentration is decreasing with time. Okay. Questions about this?
So whenever we do the rate expressions and stuff, I understand why it's -1/2, but we include that still, even though it's technically the magnitudes are the exact same, but it's still the negative version of the number.
Sorry. So why do you need to include the negative sign here? Is that what you're saying?
Overall rate expression. I know the magnitudes are the same, but like the overall rate expression, it still needs negative.
Yeah. So yeah, you do need the minus sign because, right, if you were to act like for in this example, right, if you measure, right, the rate of change of H plus, right, you get a negative value, but your rate is always defined as a positive. So you need these negative signs in for these relationships here to ensure that, right, you have the correct sign for your rate. Okay. Yeah. Right. I mean, if you want to think about just taking the absolute value of your rate of changes, you could think of it that way. But yeah, But for the sake of this class, I typically present it in this way where I just talk about what is that change and then put a minus sign if it's a reactant. But yeah. Other questions? All right. Okay. So again, some more of these questions here, right? I have some process where the rate of appearance of NH3 is reported at 1.15 moles per liter per hour. Question is, what is the reaction rate? What is the rate of disappearance of N2? And what is the rate of disappearance of H2? All right. So, right, if we want to look at first, what is the rate of the reaction? Okay. This, right? So again, I'm looking at, right, just, right, what is the rate of the reaction? Okay, right, that relationship for the rate to NH3 is going to be what? What's missing in that equation there? Right, yeah, a factor of 1/2, right? So if I take this value, right, 1.15 multiplied by 1/2, I get my rate of my reaction is, right, 0.575 molars per hour. And I look at what is the rate of disappearance of N2, right? And to find that, right, I can do a number of things, right? Now that we know the rate of the reaction, I can say, well, how is the rate of the reaction related with the rate of change of N2, right? Or I can say, how is the rate of change of NH3 related with the rate of change of N2, right? There's a number of ways you can do this. Right? We can think of the rate of the reaction or the overall rate, right? If it's the overall rate, I need factor of -1 here, right? In this case, right, these things are related to each other. I'm multiplying this by 1/2, okay? Minus sign. Now, and so it's, right, so the rate of the reaction is the same magnitude as the rate of disappearance of N2, okay? Notice that for the answers that are online and I have here, I have a positive 0.575, and that's specifically because I'm asking for what's called the rate of disappearance. So I just want to note, right, that the rate of disappearance is defined as, so this rate of disappearance is the negative rate of change of N2 over change in time. The rate of disappearance is always a positive number, okay? While the rate of change can be a negative number. So this is kind of a, annoying little minor detail thing, but in a problem, if they ask for the rate of change, that can be negative for reactants. But if they ask for the rate of disappearance, that is a positive number always, okay? So it's the absolute value of the rate of change, if you will, okay? And so just keep that in mind when asking for the rate of disappearance. It's a positive number. It's the absolute value of that rate of change, okay? And then finally, right, we can get the rate of disappearance of H2. I can relate that, say, to the rate of the reaction. Again, if I want to, right, the rate of the reaction is going to be equal to minus 1/3, right? The rate of disappearance, or the rate of change of H2, okay? And so if I use that and I multiply that on the other side, right, I get minus 3 times the rate equals the change in concentration of H2 over time. So 3 times that rate gives us 1.73 molars per hour. And again, because I'm asking for the rate of disappearance, that is the absolute value, right, the negative of the rate of change, right? Rate of disappearance is defined as a positive quantity, okay? And so if you ever see rate of disappearance, that's referring to like the magnitude, right, of that change, right? While the rate of change isn't a negative number. Again.
I have a question. Where are you getting the like the 1/2 and stuff? Like, where are you pulling that from?
The balanced chemical reaction up here. So the 1/2 is the stoichiometric coefficient. It's 1 divided by the stoichiometric coefficient in the balanced chemical reaction. Okay? So this 2 goes in the denominator here, right? And then this 3 goes in the denominator down there. So yeah, so I get these, right? And in this one, I divided by 1, right? I did like N2 divided by 1, right? And I get that 1 from the, 1 stoichiometric coefficient of the balanced chemical reaction, right? So yeah, so all of these factors of a half, a third, or whatever come from our stoichiometric coefficients in our balanced chemical reaction. Questions? All right. Oh, what am I multiplying 3 with? So let me go back to that real quick. Right. Right. So here the rate. This is the rate. Right. So we found the rate of the reaction 0.575. So this rate is 0.575. Okay. So we found that in the very first problem, right? The rate of the reaction, right, is what we solved for initially. And so that rate, right, is just equal to 0.575. So I multiply that by 3 to get them that 1.73. Okay. All right. All right. So this question, if NO2 decreases from 0.01 to 0.0065 molar in 100 seconds, the rate of disappearance of NO2 for this period is what? A, B, C, D, or E? Or would I calculate the rate of disappearance? So how would I calculate it first? Right, it's going to be what? I need, right, I got to do the change in concentration of NO2 divided by change in time. So the change in concentration of NO2 is going to be, right, 0.0065 minus 0.01, right? And then I have to divide that by the change in time, which is 100 seconds, okay? And so when you do that, right, the difference between these two guys gives you 0.0035, which is 3.5 times 10 to the minus 3. But then you have to divide that by 100 seconds. So you're going to get E here, 3.5 times 10 to the minus 5. Okay? So C is that change in concentration. The concentration happened over a period of 100 seconds. So we have to divide by the 100 seconds to get E, 3.5 times 10 to the minus 5. Question?
So in this case, you subtract 0.005 from 0.01 or the other way around?
So if I want to get so what I did is I did the final concentration 0.0065 minus the initial 0.01. Now that technically gives you a negative number, which is the rate of change of NO2, right? And the rate of disappearance is defined as like the absolute value of that. So you could have just started off with doing 0.01 minus 0.0065, and that's fine. Because in the end, you want a positive number for rate of disappearance. It's always defined as a positive number for rate of disappearance. Okay? But yeah. So. Huh? E. E. Yeah. E. Right? It's 0.0035 divided by 100, which gives you E. All right. So rate laws, okay? So rates of chemical reactions can depend on the concentrations of your reactants, and that dependence is given by the rate law, okay? So again, the rate law gives you how the rate of your reaction, right? We've been talking about the rate of the reaction. Now we're using these rate laws to describe how that rate of the reaction depends on the concentrations of your reactants, okay? All right? And so what is the general form of a rate law? Yeah, concentration of reactant 1. Then you have it raised to just some power. Concentration of reactant 2, some power, and so on and so forth. Okay. So that is the general form of some sort of rate law. It's the rate of the reaction that we've been talking about equals K, which is some rate constant. Okay. So K is a rate constant. It's unique to every given reaction, and it's temperature dependent. So it's not some uniform like value for every chemical reaction, right? The rate constant it's going to be different for every chemical reaction that we talk about. Okay. But K is a constant. It's called the rate constant. Okay. And not capital. Right. So K is the rate constant, right, in this equation. And then my reactants, right, I have times concentration of all my different reactants, the sum power, okay? The powers can be 0, 1, 2, 3, 4, right? Technically, they can be like a half or things like that, but we won't deal with that in this class. In this class, these powers are only whole numbers, 0, 1, 2, 3, so on. Okay? So for these rate laws, I can talk about the partial order of a reaction with respect to, say, reactant 1, and what would the order of the reaction or the partial order of the reaction with respect to reactant 1 in my general rate law here D equal to. What? N. It is its power in the rate law. Okay. So if I did the same thing for reactant 2, it will be N, right? And so on and so forth. And then what is the overall order of the reaction going to be equal to? Yeah, N plus M. Okay. Right, so the overall order of the reaction is N plus M. Okay, it's the sum of all the powers, right? So if there were multiple reactants here besides just the 2, right? It's the sum of all the powers gives you the overall order of the reaction, right? And then the partial order with respect to a specific reactant is just its specific power in that rate law. Okay? Let me try to highlight questions here, right? Versus our answers, right? Again, right? That is what a general rate law looks like, right? And that's what the partial order with respect to certain reactants is defined as in the overall order, okay? Right? So then in this example here, what is the partial order for this reaction given the rate law with respect to A? 1, right? 1 here, right? The power of 1 is typically not written. If it's 0, then it won't actually appear in the rate law, okay? So we'll do an example of that in a second, right? So what is the order with respect to B? 2, yep. What's the overall order? 3, right? It's 2 plus 1, so that's going to give us 3, okay? Right? 1, 2, and 3, okay? And what happens, right? What happens to the rate if I triple the concentration of A? Right? Goes up by 3 as well. It is tripled as well, right? I could say the rate is tripled as well, right? And we get that from the rate law, right? If the concentration of A is tripled, then that is tripled. So let's actually just write this out so we can show it more explicitly, okay? Right? My rate of my reaction, my rate law is defined as A B squared, right? Oh, sorry, the squared's on the outside here, right? So if A, concentration of A is tripled, right, what that means is now my rate equals K times, shoot, I didn't give myself room here, times 3 times concentration of A times B squared. Really write this right, but my A goes to 3 times A, right? That's what tripling the concentration means, right? It's 3 times A, so my rate is just 3 times K A B squared, and I compare this to the original rate, okay? It's like my new rate, right? And it's just 3 times the original value, right? And so now if B is tripled, right? If I B tripled, that means my rate here is 3 times concentration of A times 3 times B squared. Okay. Oh, that's a K. Shoot. Sorry about that. Write these things too quickly sometimes, right? So this is now 3 squared, right? Because this is a power of 2, that's 3 squared. And so it's going to be 9 times K, the rate constant K times concentration of A times concentration of B squared. Okay? So my rate has gone up by a factor of 9 when the concentration of B is tripled. Okay? Right? So again, this rate law shows you how the rate changes with changing concentration, right? Right? And so again, if I say double the concentration of A, I double the rate. If I double the concentration of B, it's going to quadruple the rate. Okay? And that's related with the fact that there's the power of 2 here for B, the power of 1 here for A. Okay? Questions about this example? All right. Right. So based on the following rate law, which of the following statements is true? So is the reaction first order in A? No. All right. So A is not true. Now let's look at B here. Is the reaction second order in A? Yes. Okay. Is it in B? Yes. Is it second order overall? No. Right. 2 plus 1 does not equal 2. Right. And C, second order in A, we said that was correct already. First order in B, we said that was correct already. And then third order overall. Is that true? Yeah, right? 2 plus 1 gives us 3. So C here is true. Okay. Right? This reaction is second order in A, first order in B, and third order overall. Any questions about the rate law, what it's defined as, what we talk about when we say something has some order with respect to some reactant, or the overall order? All right, so we'll wrap it up here today. Next time we'll start talking about the method of initial rates. Okay. Yeah, so for those who have class on Mondays, the exam is on the 28th. Those who have class on Wednesday, the exam will be the 23rd. For those who are online, you'll have to log in and take the exam Monday or Wednesday. I'll probably send out more information about that soon. Right. Don't forget to fill out your participation questions for those who are here. And if you fill them out, just leave them at the back table when you leave. Were there anything extra? Or did I run out of there?
Oh, no, yeah, there was one person.
Oh, okay. Someone who didn't get the participation question. All right, here. Just write down your name and number. Yeah, I try not to waste paper. So I'm at kind of. Okay, so yeah, once she's done, just write down your name. Number on there.
So that last quiz that we took, I think it was chapter 13 quiz.
Uh-huh.
So I took it like an hour later because I'd worked that day and I didn't realize we had a quiz on Saturday. But like if I get a 0 on it, will it be dropped or?
Yeah, so there is, let me end this meeting here.